This is Professor Corey, and this is our second lecture on advanced acid-base equilibria. In our previous lecture, we discussed acid-base reactions where both were strong, as well as reactions of a strong with a weak. By using a stoichiometry table, we were able to determine the pH of these reactions. In this lecture, we will consider reactions where both are weak, as well as identifying and creating buffer solutions. When a weak acid and a weak base react, the reaction does not go to completion and an equilibrium is formed. We then need to know if this equilibrium is product favored or reactant favored, and there are two methods to determine this. We can calculate an equilibrium expression, KEQ. So this is the same K that we've been doing all along, and the little EQ just means equilibrium. We can calculate this for a reaction if we know the Ka and Kb of the reacting species, or the reactants. The relationship is that KEQ is equal to the product of the Ka and Kb of the reacting species divided by Kw, which is 1 times 10 to the negative 14th. Using a table of equilibrium constant values, we can obtain the K values for the reactants, and in this case, our KEQ is greater than 1, so this reaction is product favored. The products will determine the pH of this system. Another method to determine if a weak acid or weak base reaction is reactant or product favored is to first identify the acid on the reactant side and the acid on the product side. For this example, we have HClO as the reactant acid and NH4+ as the product acid. If we compare the Ka for each, we can identify which is stronger. In this example, HClO has a larger Ka, so it is stronger than the NH4+, meaning it is more effective at donating a proton, so the forward reaction will occur more than the reverse, leaving us with a product-favored reaction. Either method will work to identify if the reaction is product-favored or reactant-favored. Since the reaction is product-favored, we will have more products than reactants, so these will determine the pH of the system. The next step is to compare the Ka to the Kb of the favored species. In this case, the product-favored reaction has NH4+ and ClO- as products, so we will compare their K values. Since the Kb is larger than the Ka, this solution will be basic in pH. We can determine that H2S is a stronger acid than HCN either by calculating a KEQ or by comparing the Ka values of the two acids. Once we know which is stronger, we know if the equilibrium is reactant or product favored. Since H2S is stronger, we will be reactant favored, or we can say that the equilibrium lies to the left. Recall that strong acids and strong bases completely dissociate in water. In other words, we can say that they completely form ions. We can calculate the pH using compound stoichiometry if we know the concentration of the acid, and we usually have this information given in the problem. A buffer system can resist pH change when a small amount of strong acid or base are added. This is very different than adding a strong acid or base to just water. To prepare a buffer, we need to have either a weak acid and the salt of its conjugate base, or a weak base and the salt of its conjugate acid. The reaction above represents a buffer system as long as amounts of the weak acid and its conjugate base are present. Realize that acids will react with bases, so if a small amount of strong acid is added, it will react with the base in the buffer system, which is the acetate ion, the CH3COO-. Since we're adding a strong acid, this will go to completion by reacting with the acetate ion, which will produce acetic acid. This equilibrium buffer system is able to shift and reestablish equilibrium with minor changes to the amounts of weak acid and conjugate base, such that the pH change is minor as long as only small amounts of strong acid or base are added. Using our same buffer system, the acetic acid and acetate ion, if we add a strong base, it will react with the acid, acetic acid. It goes to completion, forming the acetate ion in the process. The amount of acetic acid will be decreased slightly, and the acetate ion concentration will increase slightly. Our equilibrium will shift slightly, and the pH change will be small. Identifying buffer systems can be challenging. Remember, we're looking for a weak acid or base as well as the salt of its conjugate. The reason we need the salt of the conjugate is because the conjugate is an ion, and we don't have containers of ions available, but salts are plentiful. Example 1 will not form a buffer. This is a strong acid, and it will not form an equilibrium. Example 2 is a weak base and the salt of its conjugate acid, NH4+. This is a buffer system. We can identify the ideal buffering range by looking at the pKa of the NH4+. Example 3 is also a buffer system. The pKa of NH4+ is closer to 9 than the pKa of the acetic acid, so answer 2 is correct. This table shows some weak acid with conjugate base pairs. If we take the pKa of the weak acid, we can identify the buffered pH range. Since phthalic acid has a pKa of 2.89, it will buffer in the pH range of approximately 1.9 to 3.9. That concludes our second lecture. In summary, if we determined if a weak acid reacts with a weak base, we can determine if it's acidic or basic solution. We also introduced buffer systems and how they can neutralize small amounts of strong acid or strong base. We also learned how to find the effective buffering range of a buffer system. Next time, we'll use our knowledge of buffer systems to calculate pH changes when strong acids and bases are added. Thanks for watching our mini lecture series on the Professor's DuBois channel.